You see it's running. Oh, oh, it is working so nice, guys. You hear the sound of its operation once again. Oh. Starting with the components needed for the project, first one is the breadboard, second a ferrite core for making of the inductor, some copper coil like 20 gauge is what I'm using here, two 13009 power transistors and one universal board. Also you will need a 6 amperes diode. Take the core, place the wire through it, bend it and go clockwise until it is completely full. Make sure that you do not overlap the wires. So after completing the winding of coils on the ferrite core, your inductor is going to look somewhat like this. You can see there is no overlapping and the winding is pretty good. And I have used two wires together as one so that I can increase the current flow through the inductor, which in turn increase the current flow throughout the circuit and more charging to the inductor. Now we can cut off this wire. After that comes the part of removing insulation. So guys, starting with the construction, these are 13009 power transistor and this one is the heatsink and this is heatsink compound. Let's place it. Now that the two transistors have been mounted on a single heatsink, I'm going to tell you its use later on. Let's move on to the testing part of this circuit on this breadboard. Starting with the connection part. Safety first. Okay, so guys, it's time to connect the power supply. Okay, so inductor is here. One terminal of the switch is done in the power source. Did you see some voltage increase? Yeah. Of course, it was not going to work with a simple switch as this one. Boost converter circuits are much more than a simple circuit. This switch SW1 is not any simple switch like this, but a high-speed switching circuit, and that speed goes to even more than 100 kilohertz, 100,000 hertz. That is the frequency or even more which is going to be applied at this point. Yeah, and this time here, as you can see that I've placed this red switch, and this is the push type switch and not the continuous on switch. The meter is showing 11.64 volts, which is almost 12 volts that we are getting from the power supply. Now because I'm going to use my hand frequency, the growth is going to be slow since I'm doing it manually, but you can see that the voltage has increased from 11 point something volts to 13.87 easily. You see, 14.56, and when we do it slowly, then it is not increasing. You see, that is why high frequency is needed. Higher the frequency, greater is the increased voltage, increased speed. You see, now I've stopped and it is 16.56.
I'm feeding in 12.5 volts, sorry 11.5 volts, and here I have reached 16.5. Let's go more. Let's see how much I can do. Yeah, we have reached 19 volts. 20 more. 21. 22. No. Move to 22. Fool. 22. Oh, come on, my connections. Yeah, we can do it. Yeah. So guys, as you saw that I achieved 22 volts from 11.5 volts, which was pretty good with simple manual switching. Imagine what will happen if I connect an actual switching circuit in place of this push switch, and that switch keeps on operating at a frequency which is more than 100 kilohertz. It is going to be awesome. So with that being said, let's put all this circuit on my universal PCB boards, link for which will be provided in the description. Don't forget to check it out, please. It is a really high quality. So guys, these transistors mounted on the heatsink that you see are going to be the switch for the circuit that I showed you for the boost converter. After connecting your inductor comes your high current 6 amperes diode. So the diode has also been connected, as you can see, pretty good. Now comes the capacitor that I just used, 50 volts, 470 microfarad. So guys, as you can see that I have completed the main primary circuit for the boost converter. Now comes the part for making the driver circuit for this very switch, the transistor switch. This heatsink, 2 transistors are mounted on it, and this transistor switching set is going to be operated by the components here in this box. Starting with the circuit, the driver circuit. You see this one, the circle is 1 transistor, this is the second one, and this one are simply 2 resistors. Now I still have to decide the resistance value according to the current and voltage level of the IR emitter, which is going to send light signals to the receiver here. So guys, now comes one of the most important parts. This one, as I told you, is IR receiver, and this one is emitter, little bluish. This one is dark. So I will have to place them in this tube-like thing. So this one is going to emit light, and this one is going to receive light. There's little gap. The lesser, the better photons from this one to this one. This is done because we don't want like external lighting from our rooms or sunlight to get in contact with the circuit. It's my design. I'm not sure if others also do that, but it works pretty good for me. And I will also have to use black tape because it is still not complete. Black tape is must. Now that is one part. The other one is still left out, the other end. I think now there should be no chance of escaping of light or external light coming in. Even if so, there is no worry. I'm still going to place this heat shrink tube. Now it is completely sealed. I don't think light can enter inside it. So guys, I have also completed the driver set, okay, and this is the IR emitter and receiver pack, and this is the 1:1 inductor, and that's the primary circuit that I completed before. Now this driver circuit will give switching signals on off to the inductor of the primary circuit. With the help of those signals, this inductor is going to turn on and off, and hence it's going to perform as expected. If you look at the circuit here, I have done certain changes, and I have also like improved the circuit design. Now as I showed you that this is the driver circuit and this is the final output transistor. It has obviously three terminals: base, collector and emitter. So here the collector and emitter terminals will be finally taken out from the driver circuit and fed to the base and collector terminal of this transistor on the primary circuit. And here you see two more terminals for the driver circuit. These two are for powering up the driver circuit. This black tape that you see, that indicates negative wire, and this one is positive. So either you can connect it in parallel to the black and red of the primary circuit, or you can connect an external power supply to the driver circuit. The input voltage for the driver circuit ranges from 0 to 20 volts. So guys, I've mounted both the circuits on this wooden board. Also the supply for the driver circuit, I've connected it in parallel to the primary circuit. Now all I have to do is connect positive on this terminal, and negative on the black one, and then output is going to appear on the positive and negative. Let's test it. So guys, for the testing part, here as you can see that I am using 12 volts 5 amperes DC supply from a laptop charger. So first I'm going to measure the output terminals from the power supply. This one, that's the power supply. So guys, as you can see that the meter is pointing 0 volts. Let's connect the power supply terminals to it. And now it is showing 12.06 volts. So it's a 12 volts DC supply from the charger. Now from the 12 volts laptop charger power input, I am powering up this circuit, and you should see the display voltage. Keep watching the display screen of the multimeter. You see, instantly the capacitor charged at more than 40 volts. It's displaying 39 volts right now. Once again, so 43 volts is the max I'm getting from 12 volts input. So guys, now it's time to test it on motors. This is a 24 volts DC motor. Okay, so let's power this one up. You see it's running. Oh, it is working so nice, guys. You hear the sound of its operation once again. Oh. You see, I'm trying to stop it, but still the output is pretty good. Although the motor is small, so obviously the power of the motor itself is not very high. Actually, the transistor pack on the primary circuit is quite hot. So guys, I forgot to tell you one thing, that the transistors have negative temperature coefficient, because of which the heating multiplies if they are connected in parallel. So my advice to you is use separate heat sinks and mount the transistors on them instead of using one single heatsink, as I did foolishly because I forgot about the negative temperature coefficient part. Use separate heat sinks and then it is going to work very nice. And also I forgot one more thing. I showed you the operation of this motor with the boost converter, but I did not show you its operation without the boost converter, so that you can compare the two, with and without part. So now without the boost converter and directly from the power supply, that's the max speed. You see it is stopping slowly, so easily. You see. And the voltage is not enough. That's it. And the best part of this boost converter is that there is not a single IC that has been used for the making of this circuit. No IC has been used. It's all on transistors. So once again, I think you can compare the two. There is literally no comparison. The speed is very high for this. I'm really satisfied with the circuit. Let's move on to a bigger motor instead of this one. So guys, I found another motor, a little bigger one. It's from a reverse osmosis water pump. Again, 24 volts. So let's connect this one. Yeah, first from the 12 volts power supply directly. After that, I'm going to do the connection to the boost converter. You see, it's running so slowly. I'm feeding it with 12 volts right now directly from the power supply without the boost converter. Okay, keep watching the motor, guys. Speed has increased 3 times. This time it is running really fast. Now guys, I'm going to try and run this 360 watts e-bike motor. It is 36 volts and 15 amperes. Sorry, it's not 360. It is 36 volts, 15 amperes. So power is 36 multiplied by 15 amps. It is quite heavy. Let's run this one. First, without the boost converter. Comparison is must. Let's remove it. And yeah, that's it. Although the torque is pretty good because the motor is like really big with a big armature and coils. I cannot stop it. It's really slow. That's the point. Now here we are limited to the current from the power supply, which is only 5 amperes. At present it is a 15 amperes motor, but running at only 5 amps because it is running under no load. It's not fully loaded. So obviously it is not going to draw 15 amps. That's just common sense, right? Okay, now comes the part of running it at full power with the boost converter. Okay. Wow. You see, it is running so fast. And the torque is also very good considering the power supply that I'm feeding, although the transistors are going to heat a lot because the motor is very big here. Wow, 5 times wow. Wow, it is so cool, guys. I'm loving this circuit so much. Let's increase the load further by yeah, I have another 500 watts. Most of you must be familiar with this motor. It is available in the market. 24 volts. and the current rating is 26.7 amperes. It's very heavy. Now I'm not sure if it is going to be able to run this because the current is very high, 27 amps, which obviously it is not going to draw. I'm not bragging like without reason that it is going to draw 27 amperes from the circuit. Obviously it is not, because it is not loaded again. Okay, I keep on forgetting that first I have to test it without the boost converter and then with the boost converter. So without the boost converter, you see it's not even able to run it. Like, the power supply is not good enough for it. I think I will have to give pulse speed because the starting current is going to be huge. It is always huge. Maximum current 26 amps at the start. Now we have achieved full speed because I gave it like a current in pulses, so the power supply was not that much loaded as it was initially. Initially it was like, what have you connected? It is so big load, can't you see that I cannot handle that much load? But in pulses, yeah, okay, I can handle it, then I cannot, then I can, and finally it runs. Now guys, there is a risk since when I directly connected the power supply to this motor, it was not able to run the motor. So how is it going to be possible? Because since the voltage from the boost converter has increased, so obviously the current is going to reduce. So I'm not sure it is going to run. I don't think it is going to run, and no worries, because if I use a bigger power supply or like directly from a battery, then it will run because of the high current inductor. It is capable of handling up to 40 amps. Let's try it anyways. Now guys, the final motor that I'm going to connect, biggest that I have, no bigger motor than this one, although the current rating of it is 7.5 amperes. The current rating for this one was 26 amperes. This one is 7.5 amperes, but its voltage is 180 volts DC. Removing the boost converter, power supply terminals. It is going to run really slow. Yeah, it is at 12 volts right now. You see, torque is very good. It is at 12 volts. So you have seen the speed. Now let's move on to the part of boost converter. Circuit. Okay. Wow. Do you see the speed? It is so good. At present it is running somewhere between 35 to 40 volts, because obviously it is such a big motor, and the voltage is going to drop when loaded a little bit just at the beginning, but then it is going to be it is not going to drop then easily. I've disconnected the supply. Oops, this wire came out. Beware of the heatsink. Anyways, so guys, so guys, with that I'm finishing the video. I hope you understood the making part. So that's all for today's video. Thank you so much for watching it. Please hit like and don't forget to share and subscribe. I'm so glad to share this video with you. See you in the next one. Bye bye. So guys, your hidden question for today is, why did the capacitor blast in my previous video?